Let me take you through one last example involving free fall. When it comes to this example, there are a few differences from the previous examples. Number one, the example is going to be in imperial units. So G is going to be 32 feet per second squared for that reason. For the most part in introductory physics, most of the problems that you will encounter are in terms of metric SI units, but with a few exceptions, every now and then you're going to see situations involving imperial units. And then we have two values of acceleration in this problem to worry about. Let me read the problem to you. A rocket, initially at rest, is launched vertically from the ground with an acceleration of 64 feet per second squared for 60 seconds. Afterwards, the engine shuts off. What we're going to calculate is the maximum height reached by the rocket in part A of the problem, and then eventually what happens when it returns to the ground. Now here's how you can easily visualize this situation. Use my marker here as an example. The marker begins at rest here on the desk. Think of that as the launch pad. And then the engine fires. Think of the engine firing as the marker being in my hand as I then move the marker upwards. But then the engine shuts off after 60 seconds. That's the same thing as me just letting go of the marker. And then afterwards the object continues in free fall. So it's nothing more than describing the following. Like so, and then ultimately the rocket returns to the ground. That's what's happening in this situation. Okay, now as I mentioned, there are two values of acceleration that is present. Let's describe what happens first of all while the engine fires. What I have to calculate here are two things. I have to calculate the height that the rocket is at when the engine shuts off, and I also have to calculate its velocity at that instant. The reason why I have to do that is because those then become the initial values of position and velocity when the rocket then continues in free fall later on. Okay, let me draw up the situation. Okay, so here's the ground. Once again, we'll think of that as the origin. Okay, here's my little rocket ship. Like so. It's initially at the origin. It's initially at rest. And then it accelerates upwards. I'm going to call that acceleration a sub y. It's 64 feet per second squared. It then reaches its maximum height here at this moment after a time of 60 seconds. And when it does reach that height, right here is its final position y, and it will have here an unknown final velocity v sub y. I need to calculate these values here because, as I said, they then become the initial values for free fall a little bit later on. Now, what are my kinematics equations? Well, my kinematics equations here are the same kinematics equations as we've been working with because this is just one-dimensional motion with constant acceleration. Let me just write the kinematics equations for this situation in the following way. So here's the position equation. And here's the velocity equation. Notice that these equations are still written in terms of y because I'm using the vertical direction, but these are not the free fall equations. And the reason for this, because the acceleration is upwards here at a value of a sub y equal to 64 feet per second squared. But these are the same expressions, of course, that we've been working with throughout the entire unit. Let me now go ahead and simplify these equations. So to simplify these equations, first of all, in the position equation, plug in the zeros. Right here, the object starts at the origin, and it starts from rest. So these two terms are equal to 0, and the position equation simplifies to become the following. There's no algebraic manipulation to perform here. All that we have to do is then calculate this position. So to do so, I have 1/2 times the 64, and then multiply that then by 60 squared. So that's 3,600. And this works out to be 115,200 feet. This is not the answer to part A. This is just what happens when the rocket has shut off its engine. It's at that height, but this is the same thing as me letting go of the marker. But the marker does continue upwards in free fall. We'll get to part A of the problem in just a few moments. We also need this velocity, as I mentioned earlier, however. Let's go ahead and calculate it by using this kinematics equation where the object begins at rest. So now take the acceleration of 64 feet per second squared, multiply that by the time of 60 seconds, and then therefore the rocket's velocity when the engine shuts off is 3840 feet per second. And now the rocket continues in free fall for part A of the problem. Okay, so now we're in free fall here for part A and then eventually part B of the problem. So then therefore we have our kinematics equations. Like so, for free fall. Well, let's just carefully note here once again that this is an imperial units problem. G in imperial units is 32 feet per second squared, so be a little bit careful of that. Okay, now for part A, let's just draw it out in the following way. Okay, here's the ground, once again thought of as the origin, and then here's the rocket the instant that the engine shut off. Therefore, we have here now for this portion of the problem an initial position of 115,200 feet. And then right here is the initial velocity at this instant. That's the 3840 feet per second that we calculated a few moments ago. And now the rocket ends up here at its maximum height, where at this instant, its velocity v sub y is equal to 0. Right here, relative to the origin, is the final position vector y. That's the maximum height reached. This takes place in an unknown amount of time t. So the time t here is from this point to this point. We've already taken care of the 60 seconds earlier while the engine was firing. Okay, now let's begin with the velocity equation, where in the velocity equation, the v sub y is equal to 0. Like so. And now let's just go ahead and calculate the time t. That's the only unknown. Once again, that's the time from here to here. So to solve for the time, move the gt to the other side like so. And then divide by g to the other side to now get the time t by itself. Like so, and now I plug in. So I plug in here 3840 feet per second divided by 32 feet per second squared. This then gives me the time in terms of seconds. It's 120 seconds. That's 2 minutes. So far in the problem, we had the initial minute while the rocket engine was firing, and then after I let go of the marker, for example, it actually continues upwards in free fall for an additional 2 minutes. Now using this value here for the time, let's go ahead and calculate the final height y. In order to do so, we just plug into the position equation the following. 115,200 feet plus 3840 times 120 minus 1/2 times 32 times 120 squared. Just plug everything in. Let me do that here. So this will be the answer to part A of the problem, the maximum height reached by the rocket. So let's see, 115,200 for y0 plus 3840 times 120 minus then 1/2 times 32 times 120 squared. And the maximum height reached by the rocket is 345,600 feet. Just to give you an idea as to how high that is, there are 5,280 feet in a mile. So if I divide out by 5,280 feet in a mile, this is about 65 miles or so. At that altitude above the Earth's surface, the atmosphere has pretty well thinned out to a vacuum. That's more or less, if you want to think of it this way, where outer space basically begins. However, if you take the object and throw it straight upwards, what's going to happen to it? It's going to fall straight back down again. That's basically part B of the problem. When and with what velocity does the rocket return to the ground? You probably don't want to be standing underneath it. So let's see what happens now in part B. Okay, so for part B, what I'm going to do is just simply drop the object from rest at the maximum height that we calculated earlier of 345,600 feet. Okay, so here is my rocket now, initially at rest. When we drop it from this height, its initial position y0 is the 345,600? Yeah, 345,600 feet that we calculated earlier. Just wanted to double check that. Okay, and then the rocket will fall all the way back down to the ground. Its final position y will be 0. It will have an unknown final velocity v sub y, and this takes place in an unknown amount of time t. Is the time t here just going to be 60 seconds plus 120 seconds for a total of 180 seconds? Are we just seeing symmetry here once again? No. And the reason for that, you have to recall, is that for the initial 60 seconds of the problem, the acceleration was a different value, upwards at 64 feet per second squared. So it's not a symmetrical situation for that reason. Let's just go ahead and calculate. All right, so in order to calculate, let's begin with the position equation. in the position equation, the final position y is equal to 0, and we drop the object from rest. So then therefore the equation simplifies to become the following. Like so, and now the only unknown here is the time t, which we can solve for. So let's solve for t by moving the 1/2 gt squared to the other side first. And then cross multiply the 2 and the g over to the other side, and then take the square root. Like so, and then algebraically you end up with the following. All right, so let's see. I've got the square root here of 2 times 345, 600, and then divided by 32. Take the square root of all of that, and this is 147 seconds. So what's the total amount of time elapsed here in this problem when we take the rocket and initially throw it upwards? Well, 147 seconds is about 2.5 minutes. So then therefore it took 3 minutes to ultimately reach its maximum height. The first minute while the engine fires, an additional 2 minutes while it's in free fall, and then about another 2.5 minutes to fall all the way back down to the ground. So the time from launch to impact is just around 5.5 minutes. Okay, lastly, let's go ahead and find this final velocity v sub y by just using this expression here, where once again we're dropping the object from rest. So the velocity equation then just becomes the following, minus gt, and I plug in 147 seconds for the time. Multiply that by 32, and this ends up being negative 4703 feet per second. So just under a mile per second is its speed at the time of impact. Okay, this here concludes the examples on free fall.